So this is the last chapter that we're going to cover. It covers chemical equilibrium and phase equilibrium, okay? So we'll talk about a little bit about the thermodynamics of equilibrium. We'll talk about the equation of reaction equilibrium, and we have the equilibrium composition is the goal. What is our composition of different species, chemical species, in chemical equilibrium? All right. And then last, we'll talk about phase equilibrium. A lot of this is chemistry. If you have a good background in chemistry, this last chapter is easy. If you do not, then it's a challenge because this is all brand new material. Isn't it easier to learn something if you already, it's just refreshing your memory what you had learned before? So one thing to talk about is reversible versus irreversible reactions. And so there's a great website, University of California, Davis, and it does a pretty good job. I'm going to take you there in a page or two here. But we've been covering irreversible reactions like combustion. It's just a little arrow. You start with reactants, you go to products. But you could have a reversible reaction, meaning that you have some things on the left and you have some things on the right. Whoops. They call those reactants and products. And you could have a forward reaction as well as a backward reaction. And after some time, the rate at which it's being consumed going forward is the rate at which it's being produced going backwards. Hence, you have equilibrium. That means that molecules are still striking each other and they're still changing, but that the net change is zero and you've reached equilibrium. So here's that discussion. Irreversible reactions. Think of combustion. Combustion is an example of an irreversible reaction. You have some hydrocarbon. If that oxygen gets banged around with that hydrocarbon, it splits, makes the CO2 and H2O. It's not going back from CO2 and water back to the hydrocarbon. But this CO2, under certain high pressure and temperature, could dissociate. That's a reversible reaction. That water could dissociate. That's a reversible reaction. The way they describe reversible reactions are with this forward, with this constant, and this backward. You put them together, it's a different symbol than this. And you have then, some amount of A and some amount of B goes to C and D, or some amount of C and D goes back to A and B. So you have kind of a forward reaction and then a backward reaction. They occur simultaneously. And at equilibrium, then it doesn't change anymore. It's in equilibrium. All right. It's all to do with that colliding and then changing and breaking those bonds that hold the molecule together such that molecules rearrange. In general, you can get an equation like this. Maybe this is A, this is B, this is G and H to avoid C and D because C sometimes can be interpreted as carbon. But the textbook uses A, B, C, D anyway. The stoichiometric coefficient, lowercase, 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 and lowercase. If it's a gas, great. If it's aqueous, great. Okay? That's an AG or AQ, aqueous. Sorry about that. I'm going to try a different approach this semester than I tried in previous semesters. Previous semesters, let's get into the theory and then derive the equilibrium constant. Takes a couple pages and maybe a day or two. Here, I think most of you have had exposure to chemistry. And if you have, and you talked about reversible reactions and you talked about equilibrium, you talked about equilibrium constant, K, for that reaction. Here is the constant K. Here it's for amounts in concentration, so they use this symbol for the G. How much is G in the concentration? Could be different units like molars. And then you have an exponent, lowercase g, which is the stoichiometric coefficient in a balanced reaction equation. Then you have the amount of H raised to its stoichiometric coefficient divided by the amount of A and the amount of B raised to their stoichiometric coefficients. And that equilibrium constant then finishes out that equation. So in equilibrium, K is equal to that. And the way you use this is, this K is a function of temperature. So you find that temperature at which you have these in equilibrium, and you evaluate the K, and then you know the coefficients, and you're able to then determine the equilibrium concentrations or the amounts of each of those components. Sometimes you'll see a case of P, sometimes you'll see a case of C. The P is typically for gases, and you're dealing with partial pressures. That's related to the amount, and the partial pressure raised to the exponent. And if you put them together, you can get more of a combined equation. So sometimes you'll recall, oh, case of C, concentrations, case of P, pressures. What do we have in this textbook? Well, equation 14.24 of this textbook talks about the general equation. Look at this symbol in between. Sometimes they'll write it like this and that, but it's different than that. True? That's showing you by notation it's a reversible reaction. And we have A, B, C, D in general as placeholders for whatever components those are. And the stoichiometric coefficient, nu. Okay? A little different than the previous one. But nu sub A, nu sub B, nu sub C, nu sub D are the stoichiometric coefficients. Lot of work in between here and here, but here's the equilibrium equation. So the equilibrium constant as a function of temperature, they're emphasizing K is a function of temperature right there, is equal to Y sub C. What is Y sub C? It's the concentration, right? The molar concentration. So it would be the amount of C divided by the total amount in the mixture, the total number of moles in the mixture. It's raised to that exponent, nu sub C, just like Y sub D is raised to the exponent Y sub D, divided by Y sub A over nu sub A, etc. Then you have the parenthesis. What is that P? What do you think P stands for? Pressure. What do you think P ref stands for? Reference pressure. Guess the reference pressure. Just take a wild leap, just way out there. You're going to guess. 1 atm. 1 atm is the reference. 1 atm, okay? So if your pressure is higher than 1 atm, then you would put maybe 2 atm over 1 atm, and that's your ratio of pressures. Okay. Notice that it goes to this exponent. It's all raised to the power, where the power is this coefficient plus that coefficient minus the other two coefficients. Okay? This equation, if you take the definition of the mole fractions, y's, and you put them like this, you can then pull that n out, because that n will be to the power nu sub C, and then to the power nu sub D, nu sub A, nu sub B, and you can pull it out and you can put it right there. And so this equation and that equation are the same. They're just expressed a little different. Do you want to work in mole fractions and y's, or do you want to work in amounts, n's, like in kilomoles? So here that n is how many kilomoles of C, kilomoles of D, etc. Does this equation look familiar? Let me ask you this. Is that K a function of temperature? How do we get to K? Well, other people have reported that K out in the literature. Let me do this. Let me show you here. Here are some dissociation reactions, and they've reported in table A27. I think it's the last table that I introduce and cover in this textbook. We have covered a lot of tables, haven't we? Think about one book, and we've done a pretty good job of covering the whole book, but we didn't cover the whole book. All right? Aren't you glad? There's some sections we skipped. But one of the last tables, A27, it reports the logarithms to the base 10 of the equilibrium constant K. So here it is. They're saying log base 10 of K is the value in this table. Okay? So all these numbers, that's what they're reporting. So if you want the equilibrium constant K, you take the number out of the table. Let's grab this number right here. It's at a temperature of 3,000 degrees Kelvin temperature for the dissociation of carbon dioxide into carbon monoxide and oxygen. Can you see that's what that reaction is describing? Then that K would be 10 to the negative 0.485 because negative 0.485 is K log base 10, and that's what was stuffed into the table. So it's pretty easy to get the information out of the table. Find the reaction of interest. Some are very simple. Dissociation of nitrogen. Diatomic nitrogen, N2 dissociates into N. Here is water dissociating into hydrogen and oxygen. And here's a more complicated one where carbon dioxide with the presence of some hydrogen goes to CO and H2O. Okay. Notice the trend is, what is the trend of these numbers if I just look in this column for this dissociation reaction? Starts large negative, and as the temperature goes up, it gets closer to zero. It's increasing from large negative to not so large negative towards zero. True? It never gets to zero, at least at 3,000 Kelvin, it's still negative. But it's getting towards zero. Okay. So it's increasing. Meaning, when you look at how that K is used, you're getting more and more of what we call the products on the right side and fewer reactants. So if I have hydrogen at room temperature, there's not a whole lot of, and it's in equilibrium with itself, just pure hydrogen. There's very little H by itself. It's almost all H2. I mean, all H2. It's 10 to the minus 71. Put that in your calculator one time. That's a really small number. Okay. But as the temperature goes up, it pushes it so that there's in equilibrium more H. Now there's still, most of it's still H2, but there's some more H in the equilibrium with that mixture. Likewise, CO2, think about that. Large negative number. As I go at higher temperature, it's not as large of a negative number. What you're doing is you're seeing a shift of equilibrium. More of the products will be present in equilibrium at higher temperatures. More of the stuff on the right-hand side of that balance reaction equation. But at low temperatures, everything's on the left. It's all CO2. All right. So that's how you use this. This K is a function of temperature. Ready for the first clicker question? I get to ask your clicker question first, huh? So let's go ahead and start it. So as a reminder, this is our general reaction equation. As a reminder, this is in equilibrium. That equation's true. We got this from experimental data, that K is a function of temperature. We know what the Y's are, the P's of pressure, and the stoichiometric coefficients. We even looked at some of those reaction equations, dissociation. Okay? So the question is, does pressure influence the final equilibrium composition? Does pressure influence what the magnitude of Y sub C is, and Y sub D, and Y sub A, and Y sub B? Answer A, yes, all the time it does. B, yes, if this sum is not equal to 0. Or C, yes, if the sum does equal to 0. Or no, it doesn't. So we'll give you a few seconds to answer that question. So are we all in? I'll shut it down And we'll show the results. And the results say, you're right, it does say B, which is pretty good. Now, let me get the right answer here. So B is the right answer, and we get rid of the results. Now, explain that to me, Professor. Well, in equilibrium, think about this. If I change temperature, I'm changing something. It rearranges what the equilibrium Y's are. We talked about that, right? So if K changes, the equilibrium Y's change. It shifts it typically the way it's set up so that I get more of the C and the D, more of the PROD, the products, versus the REACT. But then they could have rewritten it the other way too, and then what's on the right now is on the left, and what's on the left is now on the right. But traditionally it's set up such that when it's cold, low temperature, these are the favored to be in equilibrium. And at higher temperature, these are now more favored to start to come into equilibrium. Okay, so that's how that affects it. Now, look at this. If I have something like the pressure is 3 atm and the reference is 1 atm, right? But then I take and multiply that. But if this exponent right here is all 0, what is 3 to the 0? Is it the same as 5 to the 0? Is it the same as 0.5 to the 0? Mathematically, anything raised to the power of 0 is 1. And so when this does equal to 0, when it equal to 0, pressure does not influence it. When it does not equal to 0, that's when it'll be like 3 to the 1.5 or 5 to the 1/2 or something. When this is not equal to 0, that's when it does have an impact. Pressure does have an impact. Okay? Let me write one equation down. We had CO2. It can disassociate the carbon, CO. I forgot the name of CO. Carbon monoxide. One is good to breathe, one is not so good to breathe. Which one would you like to breathe? CO2. Let's breathe the CO2 and exhale the CO2 and stay away from the CO. And then to balance this out, I have to put something in front of this O2, right? So for this reaction, I'm going to say right here, I'm going to line it up and we'll rewrite it up here. CO2, 1, 0, 0, to 1 CO, 1/2 O2. See that? So I'm trying to, the B's are nothing, they're just gone, okay? So for this problem, what is this exponent up here? It'll be 1 plus 1/2 minus 1 minus 0. What will it be? It's equal to 1/2. So pressure does have an effect on a reaction like this. It does have an effect. So if I boost the pressure, and I don't change the temperature, then what happens is this goes up right here. If I boost the pressure, then this ratio has to go down so the product is the same. So pressure does have an effect. And you can look and see what type of effect it has. If I boost the pressure, I'll get less dissociation of carbon dioxide. It'll push it back that way with increasing pressure. I have to sneeze. Sorry about that. Okay. Any comments on that? I know that's a little bit of insight, but I'm trying a different approach this semester. Here it is. Let's try and master it. All right.
At what point do you analyze the breakdown of your product dioxide into oxygens? Diatomic, they're not going to.
What happens is we have, we're only going to have on our final exam one equation, reaction equation. You'd have multiple, 2, 3, 4, all going on at the same time. And then that's covered in the textbook, but we're not going to get that far. And yes, then you can have more disassociation. Okay. Let's remind ourselves of the general chemical balance equation with stoichiometric coefficients. Let's remind ourselves of the equilibrium equation with the equilibrium constant K? Does temperature influence the final equilibrium composition of the components? And I'll start the clicker question and go ahead and respond. Yes, temperature does, and it does all the time, or yes, only if it's that exponent's not equal to 0, or yes, if the exponent does equal to 0, or no, it doesn't. All right, is everybody in? Let's close it down, stop, and let's show the results. And congratulations to the 93%. So the 93%, they got it right. Why do you say, yeah, temperature does influence? It does, yes, all the time. Why? Because the K is right there. It's kind of funny that when you write this equation, the effect of temperature is on one side, the effect of pressure is on the other side, and this is the answer, so to speak. The equilibrium composition is in the middle. It's just the style that it's written, okay? So remind yourself that K, sometimes they write it, that K is a function of temperature. Sometimes they just put K there, and you just have to know K is a function of temperature. How did they get it? They went out and made a bunch of measurements and reported it in the tables. All right. So let's read this problem and work this problem. I have a gaseous mixture with a molar analysis of 10% CO2, 80% CO, and 10% O2. It enters a heat exchanger. So here's my heat exchanger, and I have this mixture. It's 10% CO2, 80% CO, 10% O2, and that's mole fractions. That's the Y's, okay? And it's now heated. In the heat exchanger, there is some heating going on, okay? At constant pressure. So the pressure in is equal to the pressure out, constant pressure. So it's being heated, constant pressure. An equilibrium mixture of carbon dioxide, carbon monoxide, and oxygen exits at a temperature of 3,000 Kelvin. 3,000 Kelvin. And that pressure, they tell us, is 3 atm. 3 atm. Carbon dioxide, carbon monoxide. That's correct. Thank you. Now, the question says, determine the molar analysis of the exiting mixture. They want us to find the Y of CO2, the Y of CO, and the Y of O2. The Y of CO2 came in at 10%, the Y of CO was 80%, and the Y of O2 was 10%. But we want the equilibrium coming out. The question I have, clicker question, let's go ahead and start it, is the incoming gas mixture in a state of chemical equilibrium? Yes or no? The incoming gas mixture, is it in a state of chemical equilibrium? This is the incoming. Everybody in? We'll shut it down. Let's shut it down. And, okay, well, we have a few here and a few there. Is it in a state of chemical equilibrium? Well, the answer, so I can get rid of this box and I'll explain it. The answer is no. No. Okay. Prove it, Professor. Prove it, or show me why. What's the logic behind that? Okay, first of all, we have to know a dissociation equation. We've written it on the previous slide. I'll rewrite it here. CO2 dissociates to CO and 1/2 O2. True? All right. Now, K is equal to Y of the CO, not the CO2, Y of CO, whoops, come on now, to the power 1, Y of O2 to the power 1/2, divided by Y to the CO2 to the power 1, times P over P ref, all to the power 1 plus 1/2 minus 1. True? Sure. If it's in equilibrium, that will be true. The left side will equal the right side. True? So the question would be, I don't know the temperature, or I'd be able to go and look up that side. I don't know the temperature, but I would be able to look up that side. But can I get everything evaluated on the right side? Yes. Let's put in our numbers and see what we get. So Y of CO2, 0.8 to the power 1. If you have a calculator, please get it out and run this for me. 0.1 to the 1/2 divided by 0.1 to the 1/2. Those are going to cancel, save you a little work right there. True? And then we're going to have 3 over 1 to the 1/2. So 0.8 times the square root of 3. What do you get? 0.8 times the square root of 3. The amount of CO2 and the amount of, that does not cancel. That does not cancel. It reduces it. This is a 1 here. Sorry, I was getting a little fast there. It's divided by the square root of 0.1. True? So 0.8 times the square root of square root of 3 divided by the square root of 0.1. What do you get for that answer?
It's just over 0.1. Over 0.1. It's just over 0.1. It's not square root of 0.1.
Well, I took this one right here and I combined them. Yeah. So I'm just trying to be fast, and I'm not helping, am I? But what do you get for it? 13.86. Anybody else get around 13?
I got 4.38.
All right, 4.38?
Yeah.
4.38. It looks like the 4.38 wins. Now, what I want to do is I want to say, what is that log LOG? I can spell. Come on now. LOG base 10 of K. What is, and this K should be 4.38. So tell me, what is the log base 10 of 4.38? What do you get? 0.6? 0.642. Okay, now, if I think back on my table, I had the log base 10 of the K values for that CO2 goes to CO, I'm trying to do it too fast, CO plus 1/2 O2, right? And as a function of temperature, it started huge negative and it was getting towards 0. Did it ever, at 3,000 Kelvin, okay, it was still negative 0.84 something, negative 84. Where is it? Negative 0.485. Okay, so for this to work, it needs to be 0.642. Well, what temperature does that need to be at? Over 3,500. It's off my table. And it's coming into this heat exchanger to be heated, not to be cooled. So in order for it to have been in equilibrium, it would mean to be 4,000 or 5,000 degrees K or something. beyond our table. There's no way. There's no way. Okay. Basically, CO doesn't like to exist by itself, especially at low temperatures. And if it can link up with carbon to make an oxygen to make CO2, it'll go that way. It likes to go to CO2. It likes to be happy at CO2, not happy at CO. CO is very reactive. That's why you don't want to ingest it in your lungs. It blocks your lungs' ability to get the oxygen. Clogs them up. Okay, so this is not. It's not. There's nothing to say it's in equilibrium. Now let's solve this problem. I'm going to go to a clean sheet of paper because I messed that one up so badly. I want to determine the molar analysis of the exiting mixture. I want to find when it goes out of that heat exchanger. I want to find Y of CO2. I want to find Y of CO, and I want to find Y of O2. We know the pressure, 3 atm. We know the temperature, 3,000 Kelvin. We look up log base 10 of the equilibrium constant, negative 0.485, if I wrote that down correctly. Yep. For the reaction equation, which comes into play, CO2 disassociates the CO plus 1/2 O2. Okay. We know what comes in. We know that coming in, you have the mole fraction of CO2 coming in is 0.1. The mole fraction of CO is 0.8, and the mole fraction of O2 is 0.1. Do they sum up to 100%? Okay. So what I like to do is I like to find these Y's. Let me just, in the interest of time, tell you how I'm going to find the Y's. I'm going to find the amount of CO2 and divide it by the total amount. And I'm going to find the amount of CO and divide by the total amount, and the amount of O2 and divide by the total amount that's coming out of that heat exchanger. Okay? A little easier this way. And I'm going to use for equilibrium equation, I'm going to say that K, which is a function of T, is equal to the amount of CO raised to the power 1, the amount of O2 raised to the power 1/2, the amount of CO2 raised to the power 1 times the pressure divided by the reference pressure, 1 atm. A lot of times you just write it 1 atm. To the exponent 1 plus 1/2 minus 1, which is simply 1/2. Oops, I left one thing out, didn't I? The total N. P over P ref divided by total N. Does that look good? Okay. So let me go ahead and say this is an unknown. Right there's an unknown. I don't know it. This is an unknown. I don't know. So I have 3 unknowns in this equation. They're the 3 N's. Do you see that? So I don't know the N of CO, I don't know the N of O2, and I don't know the N of CO2. I can replace this N by the sum. The N here is the amount of CO2 plus the amount of CO plus the amount of O2. So I could replace it there. So really I have 3 fundamental unknowns. Do I know the K? Sure. The K is 10 to the minus 0.485 because it's at 3,000. Do I know the P and the P ref? Sure. It's 3. And so maybe I want to write it like that. The amount CO2, the amount CO plus the amount of O2. I have one equation with 3 unknowns. Do you see that? What mathematical strategy do I employ to be able to solve for 3 unknowns with 1 equation? Insanity or get more equations? Try it, using the insane method, which means you will never get a solution with only 1 equation, or go get 2 additional equations so that I have 3 equations and 3 unknowns. I know, I've tried the insanity method more than once. It leaves me frustrated every time. So I need 2 more equations. Well, where did this equation come from? chemical equilibrium. It came from how molecules strike each other and bust those bonds and rearrange bonds and come out different in reaction equation, dissociation reaction equation. Okay? I didn't prove it. I said I skipped that part. But what other balance equation could I use? What other equation? A carbon balance and an oxygen balance. Do I have any hydrogen balance that I could use or a nitrogen balance that I could use? There's no nitrogen, no hydrogen. So even if we did have them as players, they would be an additional equations that we could develop. But this equation's like this. What comes in must go out. Kind of simple. Balance. So what we do is we say, yeah, we're working in mole fractions, but I'd like to think about just 1 kilomole of the mixture coming in. If 1 kilomole of the mixture coming in, then I would have 1/10 of a kilomole of it being CO2. I'd have the amount of CO to be 0.8 kilomoles, and I'd have the amount of O2 to be 0.1 kilomole. See how I start that process in my mind? I say, hey, I know the mole fraction is coming in. Let me assume I start with 1 kilomole coming in. Do you think I'm going to get N total coming out, exit, to be the same as N total in? Is it going to be 1 kilomole coming out? Clicker question. All right. Is the amount in equal to the amount exiting? A, yes. B, no. We'll start it. And I have now successfully started it. You can now enter your answer. If I have 1 kilomole in, will I get 1 kilomole out? Did you have enough time to answer? Everybody in? All right, let's close it down. This is a tough equation. This is a tough equation, okay? This is a tough problem. Let me do this. Let's say I had 1 kilomole of CO2 come in, and I had it just perfect so that it all disassociated. All of it completely disassociated, such that it all went into producing 1 kilomole of carbon monoxide and a half a kilomole of oxygen. 1 kilomole CO2 in, complete disassociation. Producing 1 kilomole of carbon monoxide and 1/2 a kilomole of oxygen. 1 in equal 1.5 out. What? Let's say I brought in no carbon dioxide, but I brought in 1 kilomole of CO, and I brought in 1/2 of a kilomole of O2. I brought them in, and it's a low temperature, and I wait for it to come to equilibrium, and all the O2s gobble up with the CO2s, and they all become happy COs. All the COs and the O2s get together, and they all become CO2s. It's a low temperature. I will have 1 kilomole going out. I had 1.5 come in. I had 1 go out. This is that thing about chemistry. Some things are conserved, some things are not. What's conserved is the carbon in has to equal the carbon out. The oxygen in has to equal the oxygen out. But the number of moles doesn't have to be, because they rearranged. All right? So the answer is oh, isn't that embarrassing? How many people passed the chemistry class? Keep your hands down. Keep your hands. Oh, well. All right. So the answer was no, no, no. No, no, no. But let's do it this way. How much do I have of the carbon coming in? Well, for every amount of CO2 coming in, I have one carbon with it. And for every CO coming in, I have one carbon with it. And for every O2 coming in, I have no carbon with it. So what's on the left-hand side of this balance equation is 0.8 plus 0.1, 0.9. True? And now in equilibrium, what goes out is I have to say, whatever the amount going out of CO2 in equilibrium, there's one carbon with it, and there's one carbon for every amount of CO going out in equilibrium. Kind of emphasize this is the incoming amounts. This is the exiting amounts. That's my carbon balance right there.